So welcome to week 6 of the TA sessions on DAA. I'll wait for a couple of minutes to, so far no one has joined. Let's see if someone joins and then we can start. Okay, so no one has joined. Let me start the session. We are going to continue our discussion on strongly connected components in a directed graph. Right. So what we had discussed in the previous last few minutes of the previous session, we are given a directed graph, and the goal is to partition the vertices into strongly connected components. Okay. Now, what we mean by a strongly connected graph is strongly connected, of course, in the context of directed graphs only, that if you take any pair of vertices u and v in the graph, there must be a path from u to v as well as a path from v to u, right? That is what we mean by strongly connected graph. So given a directed graph, there can be subgraphs. Maybe the entire graph is not as strongly connected, but there can be subgraphs which are strongly connected. Now we want to identify maximal such subgraphs which are strongly connected, and that is what we mean by a strongly connected component. For instance, A alone is a strongly connected component. B alone is strongly connected, but it is not a strongly connected component because we can extend it, right? We can add one more vertex to it, and this still is strongly connected. And if I try to add one more vertex to this subgraph, right, one that contains B and E, then you will see that adding that third graph violates the strongly connected property, and therefore B and E together form a strongly connected component. Right? So I have marked all the strongly connected components in this graph. Now, if you represent each strongly connected component as a node in this graph, just compress it to a node in this graph, and something like this, right? So you have a node for this component, a node for this component, and so on and so forth. One node for this component, right? So I'll have, because there are 5 strongly connected components in the graph, I'll get another graph which has 5 nodes in it. And between any 2 nodes in this graph, I'll add an edge, a directed edge, if in the original graph I have an edge between the uh, vertices of these components, right? And we had discussed that if there are multiple edges between 2 components of a graph, right? By component, I would mean a strongly connected component. If there are multiple edges, and all of them must be pointing in the same direction, right? Otherwise, it will create a cycle and it will violate the property that this is a component. It is maximal strongly connected. So since there are, there cannot be any cycle, it's a directed acyclic graph, right? So the graph of strongly connected components of another graph G is going to be a directed acyclic graph. So so that's one property. It's a DAG, and since it is a DAG, it's going to have at least one source and at least one sink. In this particular example, there is one source vertex, right, and there are 2 sink nodes. Okay. So, hi Anant.
Hello, am I audible?
Yeah, now you are audible. You didn't attend the previous lecture, right? The class I took yesterday.
Yes, ma'am. I actually just went through it, uh, just a few
Okay.
bits of it.
Okay. So have you gone through this problem, the strongly connected component that I
Uh,
started towards the end?
no, I did not go through that. I only covered the first hour actually.
Okay. Uh, so you know this directed acyclic graph?
Yes, ma'am. I had seen the video lecture.
Okay.
Yeah,
The course lectures. Okay.
yeah, the course lectures.
Okay. And you understand topological sorting as well? So in the course lecture, they use a different algorithm to compute the topological sorting of a directed acyclic graph. And in the previous, the session that I took, I used DFS to compute the topological sorting. Have you gone through this part?
No, ma'am. I did not go through this
No.
one. No.
Okay. Um, okay. So these were just some questions to check your understanding about the DFS on a directed graph. Uh, okay, so you understand what DFS is and how do we assign the start and finish number, because that we had covered in, I think, the week 4 session, right?
Yes, ma'am.
Right, and we have different classification, the various classes classification of edges are this tree edge, back edge, forward, and cross edge. Now, we know that a cyclic graph, right? Let's say it's a directed graph and it has a cycle. It is equivalent to saying that there must exist at least one back edge, because only a back edge can create a cycle. So if I have a directed acyclic graph where there are no cycles and I do a DFS on this, I'll not get any back edge. So all the edges are going to be either tree edge or forward edge or cross edge. Okay. So One way of doing topological sorting is, what we mean by topological sorting is I want to arrange the vertices of the graph in a linear order, right? So one vertex and the second vertex and so on up to the nth vertex in the graph, so that if I take any edge in my original graph, right? Let's say there is an edge from some vertex to some other vertex. When I put that edge in this ordering, this edge direction must be the edge must be in the forward direction. So all the edges must be in the forward direction, right? So one way of achieving or finding this kind of linear ordering, which we call as topological ordering, is using DFS. So what you do is, you are given your directed acyclic graph, run DFS on that graph. Now, when I run DFS, I'll assign start and finish number to every vertex, right? So just look at the finish numbers of every vertex and order the vertices in the decreasing order of finish. Okay. So once I have this, this ordering where every vertex is, so the vertex with the highest finish time, I place it first, then the next highest finish time, and so on. So this Vn has the lowest finish time, V1 has the highest finish time. So the claim is this is going to be a topological ordering. And the reason is, if you have understood all these back edges, forward edges, cross edges, you can see this important property that it's only a back edge in a when you do DFS and you classify all the edges, only a back edge will lead to a node with higher finish time, right? So for instance, let's say this is your DFS tree. If you look at a tree edge, right, tree edge will lead me to a node with a lower finish time, because I have to finish this node first before I finish this node. So tree edge is going to lead to a node with a lower finish time. Similarly, a forward edge is also going to lead to a node with a lower finish time because it's lying on a path from root to leaf node. Okay, they have an ancestor descendant relationship. So every node here below this node, they will have lower finish time. And then when we have this cross edges, it's going to an edge which has already been finished. So cross edge is also leading to a node which has a lower finish time. Only a back edge is going to lead to a node which has a higher finish time. So the nodes which are high up in the tree, in the DFS tree, they will have higher finish time. Right? So it's only a back edge that leads to a node with a higher finish time. So since in this order, here in this order, we have the nodes arranged in the decreasing order of finish time, I'll never have a back edge. All the edges will either be, tree edge or forward edge, cross edge, and you will, all the edges will be basically pointing in the forward direction. Is this part clear?
Yes, ma'am, it is clear.
Sarvesh was present in the last lecture, yeah, right?
Yes, ma'am.
Yeah. Okay. So, so this is there. Today we are going to look at two applications of DFS. Right? So in the previous class, I just uh, started with a strongly connected component. That is one application of DFS. In fact, this is also an application of DFS, how to do topological sorting using DFS. But these are like more non-trivial examples. So we'll see two very interesting examples where we use DFS, especially those numbers, start and finish numbers associated with every node in the DFS tree, how to use those to solve graph problems. Okay, so one problem is this problem on a directed graph, where I'm given a directed graph and I want to, just one second here. Okay. Yeah, so what we mean by strongly connected graph is that if you take any pair of vertices in the graph, there must be a path from U to V and a path from V to U. Then we say that U and V are strongly connected. Right? So when we are given a graph, a directed graph, it might be the case that the entire graph is not strongly connected. Right? So what we are interested in finding is something called as strongly connected components in the graph. So for instance, this is a graph, and then I have highlighted, right? So a singleton vertex is always strongly connected, trivially, right? So A here is strongly connected. Now, is it a strongly connected component? So by component, I mean it must be it must be strongly connected and maximally strongly connected. Means that I cannot add one more vertex to this subgraph and retain the property of strongly connectedness. That is what we mean by strongly connected component. So if I take vertex A and I want to add one more vertex to it, let's say I want to add B to it, then AB will not be strongly connected. So in that way, A is a strongly connected component. Okay, so that is how we identify the strongly connected components in the graph. So one property we had discussed is that if I consider the graph of the strongly connected components of a directed graph, that is going to be a directed acyclic graph, right? We cannot have a cycle in this graph. That is so, since it is a DAG, it's going to have a source node and also like at least one source node and at least one sink node. So in this example, there is one source and two sinks. The next important property that we had discussed is, this is important and this is going to help us in, if, solving this problem. The problem is you are given a graph, you want to find all the strongly connected components in the graph, right? So one important property is, let me explain this once again because this is going to really help. Let's say I just have two components in my graph, C1 and C2. Both of these are strongly connected components, meaning that here in C1, if I take any pair of vertices, they are connected by, they are connected by paths in both the direction. And same, C2 is also a strongly connected component. Right? Now, there can be one or more edges going from C1 to C2 or C2 to C1. So let's say all the edges are pointing in this direction. So all of them I'm going to denote by a single edge. Or you can have multiple edges as well, but the crucial point is that they must be in the same direction, right? So it cannot be the case that one edge is pointing from C1 to C2, another is pointing from C2 to C1. That is not possible. So there are a couple of edges between, there are a few edges going from C1 to C2. So one important property is, if I run my DFS just on this graph, okay, this is a directed graph, and if I look at this as a singleton node, that as a singleton node, it is essentially a directed acyclic graph. So let's say I run my DFS on this graph, right? There are multiple vertices here, a few vertices here, right? Run DFS on this. I want to know, I want to look at the finish time of every vertex, right? So I look at the finish time of every vertex in the component C1, find the one which has the maximum finish time. Similarly, for every vertex in C2, I look at their finish times and look at what is the maximum finish time. Okay? So this we had discussed yesterday, that the maximum finish time of any node in C1, right, of the maximum finish time that we see in C1 is going to be always larger, strictly larger than the largest finish time that we see in the component C2. Okay, can you see why is this true?
Because the edges from C1 to C2.
There is an edge from C1 to C2. There will be two cases, right? If you want to actually prove this, there are two cases. One is, let's say I start my DFS from a vertex in C1. Then what will happen? So when you start DFS from a vertex, let's say some vertex here, U, and you start your DFS from U, then the DFS tree you will get, right? It will explore all the vertices which are reachable from U. And finally, it will come back to U. Okay, so U is going to be the root node in that case. U will be the root node. And in the DFS tree for U, I'll have all the nodes which are reachable from U. Now, which all nodes are reachable from U? Anant, which all nodes are reachable from U?
The ones which are present in C1.
So since C1 is a strongly connected component, all the nodes in C1 are reachable from U. That is correct. But since we have some, at least one edge going from C1 to C2, I also have that all the nodes in C2 are also reachable from U. Correct?
Uh, yes, ma'am.
Yes. So therefore, when if I start my DFS from a node that is in C1, I'll have one single DFS tree. And since U belonging to C1 is the root node of that DFS tree, this node will have the highest finish time, right? The root node has the highest finish time. So this is true. If I, the root node, since the root node has the highest finish time of all the nodes in these two components, this will be true. The second case is U belongs to C1. A second case is if I start my DFS from some node in C2. So then in that case, so suppose, let me mark it as V and C2 U. So let's say I begin my DFS from a node V in C2. In that case, which all nodes are reachable from V? Sarvesh?
I'm here writing only C2 nodes.
Only C2, right? Only the nodes in C2 because this is a strongly connected component. So from V, I can reach any other node in C2. And since there is no edge that takes me to C1, I cannot, reach any node in C1. So if I start my DFS from a node in C2, I'm only going to visit the nodes in C2. Okay. And then I come back to V, right? The vertex V, assign it a finish time because I'm done. But since I have not yet explored the entire graph, the graph still has vertices from C1, I'll have to restart DFS from some vertex in C1. Okay, so later I restart DFS from, let's say, the vertex U in C1, and then I'll be able to explore all of C1. Okay, so that will complete the DFS procedure. So initially, I get one DFS tree, whose root node is B. It will have all the nodes in C2. Then, since DFS has to visit every vertex in the graph, and this part is still not explored, I'll have to pick one vertex here, which is not yet visited, and start DFS from there. Second DFS procedure. Okay, so let's say I pick U, and it will give me all the nodes. It will visit all the nodes in C1 as well. And whatever edges we have, right, those are going to be a cross edges from C1 to C2. So here you can see again that which node will have the highest finish time. If I get my DFS, if I get a DFS forest, one DFS tree, second DFS tree, and then there are these cross edges, which node will have the highest finish time. If there is a single DFS tree, it is the root node which has the highest finish time. So if there are multiple DFS trees, which node will have the highest finish time?
The starting one.
Hmm, no, starting one meaning we or you.
Like in this case, see, I think you because it
You.
starts from
Yeah. See, so when I start exploring V and then I get finished with V, right? So I'll assign it a finish time. Later I start U. So anyways, the starting time of U will be larger than the finish time of V. And once I am done exploring this entire part, I come back to U and assign it a finish time. And then our algorithm terminates, right? So U has the largest finish time. Again, U is coming from the component 1. So we'll always have this property no matter where I start my DFS from, whether I start my DFS from a node in C1 or a node in C2, it will always be the case that the largest finish time will be associated with a node in C1. Okay, so largest finish time, the in words this means is max finish time is associated with a node in C1. Okay, and just think of this, let's say this was I was given a directed graph and I wanted to split it into strongly connected components, and let's say the graph just had two components. Then C1 is essentially a source component and C2 is a sink component. So what we have just observed is that if you do a DFS on this graph, the maximum finish time will be associated with a source node in the a node in the source strongly connected component. Okay.
yes, ma'am.
Yes, ma'am, clear.
Okay. This part is clear. So now let me just copy this, and now we will use these properties to design the algorithm. The algorithm to compute strongly connected components. So let me take an example and there we will discuss this part. So let me draw and just give me 1 or 2 minutes. Let me take an example. Okay, so I'm given this directed graph and I want to find all the strongly connected components of this graph. That's the problem. Given a directed graph G, find all the strongly connected components of G. Here, just by looking at the graph, can we identify the strongly connected components? Is A strongly connected component?
Yes, ma'am.
Yes, A is a strongly connected component. Okay. What about B? B alone?
Yes, ma'am.
Yes, right? Because there are no incoming edges to B. So I can go to some nodes from B, right? There are only outgoing edges from B, right? So I can go to C, I can go to E, but since there is no incoming edge to B, I cannot come back to B. So B alone is a strongly connected component. What about C?
It is not strong.
It is not a strongly connected, it's a strongly connected subgraph, right? Any singleton node is always a strongly connected subgraph, but is it a strongly connected component? No, because I can add one more vertex to it, which is that vertex.
B or F.
Which one?
Ma'am, like we can add B or F to C. So
B I cannot add. See, one vertex cannot be part of um, two strongly connected components, right? So once I have that B is a strongly connected component, I cannot add it to any other strongly connected component. So the strongly connected component actually partitions the vertices of the graph, right? So one vertex will only be a part of one strongly connected component, like the previous the example, the one that we had discussed yesterday. One vertex cannot be part of more than one strongly connected component, right? So A alone is a strongly connected component. D is a strongly connected component. B and E together is a strongly connected component. This alone is a strongly connected component. So which vertex should I add to C so that it becomes a strongly connected component?
G, ma'am.
Yeah, only I can add G, right? So it's true that C and G together is strongly connected because I can go from C to G and there is also a path from G to C. So they form a strongly connected subgraph. Is that a strongly connected component? Can I add one more vertex to C and G and still have the strongly connected property true?
Yes, ma'am. Like F. I think C, J, C, F, G.
C, F, and G. So if I take these three vertices, right, C, F, and G, then what happens is from F, I can go to C. There is a path from F to C. There is a path from F to G. But is there a path from G to F?
No.
No, right? So I cannot add F. I mean, if I add F, these three vertices, they are not strongly connected. Right? So if you observe it, if you take any other vertex also, let's say J or F, which are directly connected to C and G, you'll see that you will not be able, if you add these vertices, then the resulting subgraph will not be strongly connected. So you have to keep adding the vertices as long as the strongly connected property is true. The moment you see that strongly connected property is not maintained, you say that, okay, these vertices together form a strongly connected component. Clear?
Yes, ma'am.
My screen is not visible, right? At least I cannot see my screen. Can you see the screen?
Yes, ma'am.
Okay. Okay, now I can see. Yeah, so C and D together is one strongly connected component. How do I rotate it? So bad. I did not have this issue with the other tab, only this tab. Okay, fine. Okay. So C and G together form a strongly connected component. Uh, what other components do you see in this graph? Okay, let me ask specifically, what about D, H, and I?
Ma'am, DHI together forms a component. Like,
D, H, and I, they together, so if I just have these three vertices, because it's a cycle, if if take any pair in this, any pair of vertices, you will be able to reach from one vertex to the other vertex. That is true. Can I, so it's a strongly connected subgraph of the entire graph. Can I extend it any further? Can I add more vertices to this and still have the strongly connected property true? You also see that this part, right? This is also a cycle. E to I to J, J to F, and F to E. Okay? That is also a cycle, right?
yes, ma'am.
Yeah. So this is also strongly connected. This is also strongly connected. Can we say something like, can I merge these two and say that the entire set of remaining vertices is a strongly connected component?
Yes, ma'am.
Yeah, because it's something similar to what we had discussed over here, right? So here I had told you that if I take two strongly connected components in my graph, then all the edges between C1 and C2 will be in the same direction. We cannot have something like this. All the edges must be pointing in the same direction. So one case is if I have two, if somehow I say, okay, this is one strongly connected component subgraph, this is another strongly connected subgraph, that means there are some edges which are common to them, then the entire thing must be strongly connected as well. Okay, so something like that is happening over here. D, H, and I is strongly connected. This part is also strongly connected. I is common to both, means I must be able to reach from any vertex here to any vertex here in both the direction. So for instance, if I want to go from D to J, I'll go via D to H, H to I to J. And if I want to go from J to D, I'll go from J to F, F to E to I, and I to D. Okay? So this is true for every pair of vertices in this subgraph. And therefore, these vertices together must form a separate strongly connected component. So that's the final strongly connected component we have in this graph. So is this part clear? At least how do we identify strongly connected components in a graph? Like just by looking at the graph. Now we have to design an algorithm for this. But at least the notion of a strongly connected component is clear to all.
Yes, ma'am.
Ma'am, why can't we connect CG and the bigger strongly connected component?
CG and okay, this you mean this one and this bigger one?
Yes, ma'am.
Okay, so if you look at the edges between this component and that component, what all edges I have? This one, this, and this. All these edges are, so let's say this is component 1 and that is component 2. Right? Now look at all the edges between the component 1. When I say edges between C1 and C2, I mean between vertices in C1 and vertices in C2, you will see that the edges are in one particular direction. They are going from C1 to C2. So that means from a vertex in C1, I can go to a vertex in C2. But then if I pick a vertex in C2 and I want to go to a vertex in C1, that is not possible. And for a strongly connected property, I want paths in both the direction. I must be able to reach from U to V as well as from V to U. That is what
Okay, ma'am.
strongly connected means.
So, ma'am,
Clear? Huh.
if even if one edge was in the reverse direction from C2 to C1, then we
Then
could
I
have.
would have, yeah, then C2 alone is not as strongly connected. It is strongly connected, but it's not a strongly connected component. This also would have been a strongly connected, but not a strongly connected component. I would have to merge these two and say that, okay, together they form a strongly connected component.
Okay, ma'am, it is clear.
Okay. So once you identify the strongly connected components, you will see that if you take any two strongly connected components and there are edges between them, they all must be in the same direction. So the moment you see that, oh, I'm seeing two edges going in different direction, it means you haven't identified the components correctly. Okay. So now let's look at this problem, right? Uh, now I just don't want to, given any graph, I want to identify all the strongly connected components. I want to design an algorithm for this problem. Any ideas? So first of all, the graph of strongly connected components is a DAG. So we should be able to identify source and sink strongly connected components in these graph, right? For instance, here A is a source SCC, source strongly connected component. B is also a source strongly connected component, right? This D to J, right? DEFGHI, this entire thing, is this a source or sink or none? Is this component a source component or a sink component, or it's neither source nor sink?
Ma'am, it might be needed because like from A and B, there is coming down and it's also going to
Yeah.
G. So
Yeah, so we have edges which are coming to this component, and there are edges which are going out from this component, right? So this is neither a source nor a sink. And CG, if you see, all the edges uh, are incoming to CG. That means it's a sink strongly connected component, right? So since if I look at this graph, the graph of strongly connected components, that is a directed acyclic graph, it will have at least one source and at least one sink. And from this property, mm, it is clear that if I run my DFS on the graph of strongly connected components, then the maximum finish time will be associated with a node in the source vertex. C1, I can actually write it as with a node in a source vertex. A source is strongly connected component. Okay, so what it means is if I do a DFS on this graph, entire graph, and you assign start and finish time to every number, you do DFS and assign start and finish time to every node in this graph, then you will realize that the node which has the highest finish time is going to be either A or B, because they are part of the source strongly connected components. You can try this. Okay, and the proof actually follows from this property. Is this part clear?
Yes, ma'am.
yes, ma'am.
Yes. Now let me tell you one thing. Suppose I start my DFS from a sink node in this graph of a strongly connected component. Let's say, see, our goal is to identify all the strongly connected components. Let's say my goal is to identify just the sink strongly connected components in this graph. So what I can do is I can start my DFS from the vertex C or the vertex G, which are part of the sink node. So suppose I start my DFS from C. Which all nodes will I explore? Will I be able to explore? If I start my DFS from C or G, which all nodes will I be able to explore? All the nodes which are reachable from those two nodes. Right? Suppose I start from C, I will only be able to explore the nodes which are reachable from C. Which all nodes are reachable from C?
I'm only G is reachable.
Only G is reachable.
And then
C and G,
C
right? C is C
and
and
G.
G.
Yes.
So if I do a DFS from C, I'll get a DFS tree which will only have C and G in it. That means if someone can give me a node which is in a sink strongly connected component, and I do my DFS starting from that node, I will be able to identify this sink strongly connected component. Correct?
Yes, ma'am.
Is that clear to all?
Yes, ma'am.
Yes. So the first question that we should ask ourselves is, how do we identify a node in sink strongly connected component? We know how to identify a node in source strongly connected component. And that is why if we do a DFS on this entire graph, we know that the node which will have the highest finish time is going to be in a source in strongly connected component. What we really want is a node in a sink strongly connected component. So what we can do is we will keep the graph and reverse all the edges, right? So let me reverse the edges of this graph and see what it gives us. So I'll have the same graph, just that the edges, I'm going to reverse their directions. Oh, that does not matter. For every edge, I'm going to reverse its direction. And now you will see something interesting happening. So I was given this graph. I reversed the edges of the given graph. Do you think the strongly connected components will change or they will remain the same? The strongly connected components of the original graph G. Let's say I have this is my graph G, and this is the reverse of this graph GR. Is it true that both have the same set of strongly connected components?
Yes, ma'am. Both
That
are
will be true.
same.
Yeah, we have just changed the direction, right? So if I pick this strongly connected component and reverse all the edges, it's going to remain as a strongly connected component. It's if I pick these two strongly connected components, reverse all the edges, and find all the edges initially were pointing from this component to the other component. Now they will be pointing from C2 to C1. Right? So when I reverse all the edges in the graph, the set of a strongly connected component is not going to change, which means that the answer is not going to change, right? So whatever is the solution for G, the solution remains the same. So I reverse all the edges, right? And since the strongly connected components remain the same, what can we say about the source and the sink strongly connected components now? Do they change? I'm not able to draw this properly. So in the original graph G, these two were source SCCs. This was the sink SCC. What happens in this graph G of R, the reverse graph?
Source and sink are reversed.
Reversed, right? So this becomes the source strongly connected components. They become sink strongly connected components. Note this. A has all the edges are coming towards A. So this is a sink meta node now. Similarly, all the edges are coming towards this. Earlier, they were leaving from this. So this was source. Now this becomes sink. If I look at this one, all the edges are leaving this component. That means it has become a source SCC now. Okay. And the one which was neither source nor sink, it will still remain the same. It won't be a source or a sink node. If I run DFS on G of R, what is the important property that we can use? Suppose I run DFS on GR, what do I get? Which node will have the highest finish time? Yes, Sarvesh.
Like it depends on from where we start. So okay, in the second case, I think from CG.
Yes. No matter where we start, no, this property that we had discussed, that the maximum finish time will always be associated with a node in a source strongly connected component, means that if I run my DFS on G of R, the maximum finish time will be associated with either C or G, because those are the nodes in the source strongly connected component. Correct?
Yes, sir.
Yes. And I have identified a node which is actually there in the sink strongly connected component of G. That is what I wanted. Right? So you run your DFS on G of R, pick the node which has the highest finish time. It will lie in the source, in a source strongly connected component in GR, which means that it lies in a sink strongly connected component in G. Now you go back to G. From that node, you run DFS. you will be able to identify one strongly connected component. Is that clear to all? Like how to identify one strongly connected component?
Ma'am, it was a doubt.
Hmm.
So, in the G graph, like which is up,
How?
so in that on the high this one the finish time, the one with maximum finish time will be A or B, ma'am. Like how do we know?
Yeah, here it will be either A or B, but we don't run our DFS initially on G. We will run our DFS on G of R, the first DFS. That will give me a node. I mean, the node with the highest finish time will lie in a source strongly connected component, which will be either C or G. I go back to my original graph and I know that uh, if this was a source SCC, here it is a sink SCC in the original graph. Now I run DFS on G starting from a node in the sink SCC. And I will only get C and G because that is what we had discussed, right? If I start my DFS from C or G, I'm only going to explore just these two vertices. So that will give me one strongly connected component.
Okay, ma'am.
Is there still some doubt?
Ma'am, like that's what like it looks a bit confusing, but
Hmm.
then now it's clear, ma'am. Like why are we changing the source and
Source and
sink?
sink.
Like,
Okay, let me repeat this again. Let me repeat this. So see, I am given this graph. The problem is to identify all the strongly connected components. Okay. Let's say for now, our goal is easier. I just want to identify, they can be one or more sink strongly connected component. I want to identify one sink strongly connected component in my graph. Just one sink SCC. Okay. So let's say in this graph, there is only one sink SCC. I want to identify this. So for that, if I just want to identify this strongly connected component, someone should tell me start your DFS from C or G, correct? So someone should give me that extra information. Start your DFS from C or G, then only you will be able to identify this strongly connected component. That part is correct?
yes, ma'am. Yes.
Yes. So now I want how to identify that I must start my DFS from C or G. Okay. So the thing is, if I reverse all the edges in this graph, right? So I get this GR, the reversed graph. Then this sink strongly connected component will become a source strongly connected component. Okay. And I know using this property that in a graph, if I run my DFS, assign finish time to every node in the graph, the maximum finish time will always be associated with a node in a source strongly connected component. So what happens is if I run my DFS on G of R, the maximum finish time will be associated with C or G. So let's say it's associated with C. Let's say the maximum finish time is assigned to C. So I know that C must lie in a source strongly connected component in GR, which is equivalent to saying that C must lie in a sink strongly connected component of G. So that, that question that someone will give me a node from a sink strongly connected component is now answered. How can someone give me a node from a sink SCC is take the reverse of the graph, run DFS, pick the node which has the highest finish time. That node will lie in a sink strongly connected component of G. Is it clear now?
Yes, ma'am.
Anant, is this clear?
Yes, ma'am, it is clear.
Okay. Now, once you have identified one strongly connected component, how do you identify the remaining strongly connected components?
And based on the directed lines, I mean the edges.
Based on, no, now what you do is delete this forget about this part. Okay, the resulting graph will still be a directed acyclic graph of the strongly connected components. So forget about this part. Okay, these are still source strongly connected components, and you will notice that this becomes a sink strongly connected component now. If I
Yes,
delete
ma'am.
these two vertices, right, then this becomes a sink. So now I want to identify a vertex in this sink strongly connected component. Do the same thing. Go to GR, look at the node which has the highest finish time. That node will lie in the source strongly connected component here. Come back, run a DFS from that node. You will be able to identify exactly this. Okay, so you can recurse. Once you know how to identify a sink strongly connected component, you can just delete that part and recurse. Or you need not explicitly delete it. Rather, what you do is, so initially I picked up the node which had the highest finish time, let's say C. So I come back to G, run my DFS from C. I'll be able to explore just C and G. So I claim that, I output that C and G together form one strongly connected component. Then I will pick the next vertex which has the highest finish time in G of R. So I will run DFS on G of R just once, right? So we can order all the vertices in the decreasing order of finish time. So initially I picked C. Next I will pick the vertex which has the uh, second largest finish time after removing C and G. So forget about C and G. Look at the remaining set of vertices. Whichever has the highest finish time, go back to G, run your DFS from that vertex. You will be able to identify another strongly connected component. That is how you have to proceed.
Okay, ma'am.
Okay.
And this approach of decreasing finish times, this is a different approach from the one that we are recursively trying to change the source and sink.
So that will require more work. Like that was just for the explanation part, that I can recursively find all the strongly connected components in that way. But the problem is, you will have to do DFS multiple times on G of R. So for every component, once I've identified this component, then I will delete it explicitly. Then again run DFS on G of R, pick the node which has the highest finish time, go back to G with this part deleted, run your DFS. So you'll have to do DFS multiple times. That's the problem. And DFS is expensive, right? DFS, how much time does that take? It's linear in the size of the graph. So if you want to keep it simple, run DFS on G of R once, sort all the vertices in decreasing order of finish time, and then pick the vertex with the highest finish time, run DFS here. You'll get one SCC. Now whatever SCC you have got, strongly connected component, that will have a few vertices. Forget about those vertices here. Of the remaining vertices, again pick the one which has the highest finish time, go back to G, run DFS from that node. You'll get another strongly connected component, and that way you can uh, find all the strongly connected components.
Okay, ma'am. Clear.
Okay.
Okay,
Okay.
ma'am.
So yeah, so I'll take a short break here. So today, since I want to complete another application of DFS, that is also very interesting. I'll take, shall we resume at 4:10 in 4 minutes? Is that okay?
Yes, ma'am. Yeah, it's
Okay.
okay.
Yes, ma'am.
Okay. So we'll join back at 4:10. You people stay connected. Yes, so I have just written the algorithm also here in case you want to implement this strongly connected component algorithm. So you'll have to define DFS procedure, right? Simple DFS. You run DFS on G of R starting from any node in G. Right? Then you order them in the decreasing order of finish time. And now, whenever you see that a node has not yet been visited, just invoke DFS on the original graph starting from that vertex. And whichever nodes are explored in that particular DFS call, you output that as a strongly connected component. So, right. So this will give you all the strongly connected components in the graph. So you can try to implement this. And as an exercise, I would suggest that you actually run this execute this algorithm on this example graph. Right? So you have the reverse graph, run DFS on this, you'll be, and then uh, sort them in the decreasing order of finish time. First observation will be that the highest finish time will be either C or G. Go back to G and find all the strongly connected components. Okay. Is my screen always visible or there are some issues in between?
It is visible.
Visible. Okay. Now let's look at the other problem. Okay. Now we will have an undirected graph. Let's say it is connected. And what I want is something called as an articulation point. Okay. So I'll explain what the problem is, what an articulation point is in a graph. Let me first write the problem statement. Let's say I'm given an undirected graph. And assume that it is connected. I want to find all the articulation points in that graph. So what I mean by articulation points is find all the articulation points. These are also known as cut vertices in the graph. What I mean by cut vertex or articulation point is, suppose I'm given an undirected graph. If I remove a vertex from that graph, the graph can become disconnected or it may stay connected. Right? So if after removing a vertex from a graph, the graph disconnects, then we say that it's a cut vertex or an articulation point. Okay, so for instance, here's a simple example. Does this graph has an articulation point? Let's say these vertices are A, B, C, and D. Is any vertex a cut point? Cut point meaning if I remove that vertex, then the graph becomes disconnected.
Ma'am, C is B and C both would.
If I remove D, right? If I remove D, then so removing a vertex means that I have to remove the vertex as well as the edges which are incident on that vertex, right? So I'll have to delete these two edges as well. So if I remove D, what happens is my graph is still connected, isn't it?
Ma'am, either B or C.
No, right? So even if I remove B, still what I'll be left with is A, C, and D. They are still connected. Remove C, I'll have to remove all three edges. The remaining graph will be A, B, and D. The graph is still connected. So none of B, C, and D are uh, cut vertices. Even A is also not a cut vertex. You remove A, you will have this triangle graph, which is connected. I hope all of you understand what a connected graph is, right? What do we mean by a connected graph? An undirected connected graph? That if you take any pair of vertices in that graph, there must be a path from, so let's say you take any pair of vertices U and V, there must be a path from U to V. So if that is satisfied for every pair of vertices in the graph is a connected graph.
Ma'am,
Ma'am, but
here,
we are losing one of the vertex. So does every pair of vertex, that definition, does it hold here also? Like if we remove a vertex, then we are not getting every pair of the original graph's vertex.
Mm-hmm. So what the definition of cut vertex is, if I remove a vertex, and the resulting graph after removing that vertex is still connected. So then my definition of connectedness is with respect to the remaining graph. So every pair with respect to the remaining graph is connected or
Oh,
not.
yes, ma'am. It is clear. Yeah, clear. It is clear.
Clear? So Sarvesh, you were also saying something?
ma'am, I had a small doubt in
Hmm.
the connected graph
Hmm.
concept. So here A and D are not connected. Still,
They
is
are
it?
connected, right? A and D, there is a path from A to D. By connected, we means there must be a path. It's not that there is an edge, direct edge between A and B. There must be a path between A and B. It is connectedness, even in the directed graph, when we are saying that U and V are connected or strongly connected rather, means that there is a path from U to V, a directed path from U to V and a directed path from V to U. It was the case of directed graph. I must have path from U to V in both the direction. In case of undirected graph, there is no notion as such like strongly or weakly. They are either connected or disconnected. So I say if U and V are connected, if there is a path from U to V. They are disconnected if there is no path from U to V.
Okay, ma'am.
Okay, so this graph is connected. And now if I look at any vertex in this graph and I remove that vertex from the graph, the resulting graph is still connected, right? So this graph has no cut vertex as such. But now let me add a few more vertices or edges to this graph. So let's say I add two more vertices. And this is E and F. This graph has a cut vertex. First of all, is this graph connected? Entire graph? It's very easy to identify whether a graph is connected or not.
Yes, ma'am,
Mm,
connected.
ma'am,
Yeah,
it is
this is connected, right? Every pair has a path. No, whichever pair you take, right? There is a path from one vertex to the other. Now, is there a cut vertex in this graph? Padma Priya, is there a cut vertex in this graph?
Yes, ma'am.
Which is the cut vertex?
But I have still doubt.
Okay, Anant, is there a cut vertex in this graph? Sarvesh?
Ma'am, I think C is a
Yeah, C is a cut vertex, right? If I remove C,
Sorry, ma'am.
yeah,
There's
it's
network
fine.
issues. Sorry. I think it's C
Yeah,
because
if I
because
remove
A,
C,
B, D, and E, F gets disconnected. So
when I remove C, so what happens is I'll have to delete all the edges which are connected, which are incident on C, and now your graph disconnect. You get two different components in the graph. There is no path from E to D. There is no path
so
from a vertex in this component to a vertex in this component. So removing C disconnects my graph, and therefore C is a cut vertex. Is this clear?
yes, ma'am.
Anant?
Yes, ma'am, it is clear
Yeah.
now.
So the notion of cut vertices is clear. So there can be one or more cut vertices in a graph. The goal, our goal is to find all the cut vertices in a graph.
Ma'am, now we can remove B also, ma'am. Then
Yeah. So once you have, uh,
then if we remove B also, then A, D will not
no, but
connect.
then B is a cut vertex for this graph, not for the original graph.
Yeah,
For the original graph, there is only one cut vertex. Okay. And we
yes.
want to find the cut vertices of the original graph G.
Okay.
This is after removing, this is not G. Okay,
Okay.
this is G minus C. Okay, so this will have some other, this can have new cut vertices, but I just want to find the cut vertices of the original graph. Okay. Let's say I had one more vertex here. Then do you see any other cut vertex in the original graph? Let's say this is my graph G.
Also, we can take D,
Yeah,
C, and
now
D.
D is not C and D. Yeah. So C is the cut vertex. If I remove C, in that case, I'll have D and then G. And if I remove D, then again, I'll have the components as this is G minus C. And if I remove D, then we'll have if I remove D, then I'll have again two components. One is this, the other is just G. So D is also a D is also a cut vertex.
Ma'am, now we shouldn't represent both removing C and D at a time.
Sorry, what is the question?
In that graph G, we can
Mm-hmm.
remove both C, D at a time and we can draw the graph, or else we need to remove both.
No,
If
no. So, so there is something called as two connectedness, three connectedness, where you want to simultaneously remove a set of vertices. Here, our goal is to find a cut vertex. That means at one instant I'm going to remove only one vertex, right? So I
okay,
can identify that C is an articulation point. That time I don't care about other articulation points. I'll remove C and see that it must give me at least two components, right? Two or more components. Similarly, then I in the G in the original graph I see that D is also a articulation point, because if I remove D again my graph gets split into two or more components. Okay, so at least
okay,
two components, right? So the problem definition is clear to all,
yes, ma'am.
Anand and
Yes, ma'am.
Sarvesh? Yeah. So now let's,
yes, ma'am.
okay, dear. So now we want to again, we want to use DFS to find all the cut vertices in the graph, right? And if you remember from the previous lecture that if we run DFS on an undirected graph, uh, we can only have tree edges in the DFS tree or back edges, right? We cannot have, so back and forward edges will be the same, which we will refer to as back edges, and there cannot be any cross edges in an undirected graph. Means when you do a DFS on an undirected graph, every edge gets classified as a tree edge or a back edge. We don't have the notion of forward edge or cross edges, just tree and back edges. The tree edge, which are used to explore the vertices of the graph, and back edge, where we see that we come to a node and we see that there is an edge going back to a vertex which has already been visited, right? Now using DFS, I want to identify all the cut vertices of G. Right? So let's understand how DFS will help in identifying the cut vertices. Right? So I have my graph G, whatever graph is given to me. I run DFS on that graph, and now I want to study the DFS tree that I get, and based on those edges, right, tree edges and back edges, I want to report whether a node is a cut vertex or not. Okay, so let's say I run my DFS and I get a DFS tree. Let me draw a DFS tree.
Mom,
It will,
did you like you're saying back? It means to be backtracking.
no, so
Actually,
now
this is my
at
first
this point I
lecture,
cannot,
mom.
yeah, so you should have gone through, because I have explained this multiple times, and the thing is, due to medical reasons, I'll not be available to take classes for the next few days. What I would suggest is you go through these lectures again.
I
Okay.
couldn't open those lectures, mom. As today is Independence Day, so I was
No,
available at
YouTube,
this
in
time. So
YouTube, I have uploaded all the lectures.
okay, ma'am. That
Okay.
actually that link is not opening, ma'am, which I had
Eh,
got on my email.
are others able to access the YouTube videos?
I'll see
Yes, ma'am.
directly.
I'm
Yeah,
able to access using the
yeah, I
Excel sheet.
think, yeah, everyone should be able to access. So, Padma, just try it. Yeah.
This one, thank you. Actually, this is my first time taking NPTEL course, so I
Okay.
was not aware.
Yeah, so they must be sharing an Excel sheet.
Everything.
There, every link will be there. So let me now
Okay.
finish this. Okay. So this is interesting, and I don't want to extend it to the next class.
Sure.
Yeah. Okay. Yeah, so let's say so first thing is, since my graph is connected, if I run my DFS on the graph, I'll have one DFS tree. It will not be a collection of trees, right? There will be just one DFS tree because it is connected. Whatever vertex I start with, I must be able to reach every other vertex. So let's say that the root node is U. Okay, that's my root node of the DFS tree. Now, there are two possibilities. Either this DFS tree with the root node U will have one child, right? And then we'll have a subtree rooted at that child. Or the other possibility is that the root node has two or more children. They can be more than two as well. Let me just draw two children. Now, can you say, quickly answer whether the root node, the node U I have here, is a cut vertex or not based on the tree that you obtain, based on the number of children it has? I'm going to write some of the important observations that we can make from the DFS tree on the undirected connected graph G. So first of all, I want to answer the question, when is the root node a cut vertex?
Ma'am, when it has children on both the sides, then it is a cut vertex. Like
Okay,
and otherwise it is not,
it is
because the
not.
graph is still connected in the other case where it has only children
The
on one
one,
side of
yeah,
the
so
tree.
there is case one where U has only one child, the root node has one child. And the second case is when the root node has multiple children. There are only these two cases. So let's consider this case one where U has only one child. In this case, our claim is that U cannot be an articulation point. Does everyone see that? And remember, there can be back edges as well, right? So from a node, somewhere in the subtree, I can have an edge coming back to you. That is possible, right? It is possible over here as well. From both the subtrees, I can have back edges to you. So first claim is, if U has a single child in the DFS tree, U cannot be a cut vertex. Does everyone see that?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Sarvesh, yes. And if U has indeed has like two or more children, then U has to be a cut vertex. The root node has to be a cut vertex, right? So if I remove U in this case, I'll remove all these edges, right? And clearly it will, the graph will get disconnected into two components, at least two components. If it has multiple children, it will get, if it has three children, it will get decomposed into three components. The graph will get disconnected. Okay. Here, if I remove U, I will still have just one component, because a subtree is a connected component, right? That is how you define a tree. It must be a connected graph. That is one property of tree. So the first observation is, root is a cut vertex if and only if it has two or more children. So that is our first key property. The root node is a cut vertex if and only if it has two or more children. Okay. Now let's look at another simple case. What about the leaf node? So in this DFS tree, you have one root node, exactly one root node. You can have multiple leaf nodes, right? The leaf nodes. What about the leaf node? Can leaf node be, if you pick one leaf node, can that be a cut vertex?
Ma'am, like for example, in the G graph, C is if C is not a root node, if C is a leaf node, then it is a cut vertex.
But is it possible that C will be a leaf node? Run DFS on this graph. Okay, this is actually a nice question. Run DFS on this graph. No matter where you start with. Okay, so don't start with C, and otherwise C will be the root node. Let's say you start with A or B or D, G, any other vertex. Is it possible that C lands up at the last level of the tree as a leaf node? So let's say I start my DFS from A. From A, I'll go to B. From B, I can go to D, D to G. I come back to D, come back to C. From C, I'll have to visit E or F.
Oh yes,
I mean,
yes,
that
ma'am.
is
C
one
is not.
way of, yeah, C can never be a leaf node. Similarly, D can never be a leaf node, no matter where you start your DFS with. So if you think about your DFS tree, right? Let's say this is my leaf node. This can never, if you delete this node, it will never be able to disconnect the graph. So the leaf node can never be a cut vertex. All you will have is leaf node is connected to its parent. It might have a back edge going to an ancestor, but if you remove it, nothing is going to disconnect. Okay, is that clear?
Yes, ma'am.
Yeah. Leaf node is not a cut vertex. And so if you are given a graph and you are already able to identify the cut vertices, you should be able to see that the cut vertex can never happen to be a leaf node in the DFS, no matter where you start your DFS with. Okay. Now, what about any other node in this graph? So we have discussed the case of root nodes. Okay. The root node is clear. Root node can be a cut vertex or not, depending on how many children it has. Leaf node is never going to be a cut vertex. Now we have to uh, decide about other nodes in the DFS tree. So what about the other nodes which are not root node or leaf nodes? How do we identify whether that node is a cut vertex or not? Let me draw a figure first, and then then I'll explain. This part is important. The third case. So let's say I have a node. So I have a root node first of all. I'm not giving it any name because I'm not going to use it. And there's a path starting from the root node. And I reach a node which is neither a root node nor a leaf node. Let me call that node as U. And since U is not a leaf node, it will have at least one child. Let's say it has a number of children, right? So let's say it has two childrens. We say V1 and V2. Okay, and V1 and V2 can have subtrees. They can be a subtree which is rooted at V1, subtree rooted at V2. It can be empty also. Right? V1 or V2 can be leaf node as well. But the main thing is U is not a root node. It is not a leaf node as well. So it will have at least one child, and it will have at least one ancestor as well. Now look at the children of U. Okay, so what we want to decide is U a cut vertex or not? That is the question we want to answer now. Okay, so we look at its children. Look at the subtrees rooted at those children, the entire subtree, all the lower nodes here. See the back edges which are coming from these subtrees, right? So either from V1 to some ancestor, or some node here to the ancestor of U. So look at all the back edges. Let me draw those back edges. So some back edge might just from the subtree can go to V1. Okay. There can be a back edge going to an ancestor of U. There can also be a back edge from another child coming back to U. Okay. There can be some back edge going to an ancestor again. So a number of back edges can be there. Okay. So suppose this was the scenario. You had a vertex U. It has a number of children, and for every child there is a subtree associated at that child, right? You look at all the back edges which are coming from that subtree, and what you observe is that there is at least one back edge which is going to an ancestor of U. Similarly, you look at the second child and you look at the subtree associated with that child, right? See all the back edges which are coming from that subtree, including vertex V2 as well. See, there is one back edge which is going to an ancestor of U. If this is the case, that there is at least one back edge which is leading me back to an ancestor of U, in that case, can U be an articulation point? So this is the scenario. For every subchild of U, there is a back edge which is taking me back to an ancestor of U. In that case, can U be an articulation point?
Ma'am, it cannot be because the graph is still connected.
It will still be connected, right? So here, for instance, if I remove U, I'll have to remove all the edges which are incident to U. Graph is still connected. Do you see that? Does everyone see that? And the reason is because of the presence of these edges.
Ma'am, but the root is still disconnected from the leaf nodes, ma'am.
No. So root, I come to this node and then I come to this node. So this part is connected. Similarly, from the root, I come to this node and via this edge I am connected to this node. If you look at these two subtrees, let's say in general V1 and V2, are they connected? Yes. I'll go here, then take this back edge, then take this short path, take this back edge, come to V1. So everything is connected.
Okay, ma'am.
Okay. So if this is the case, then U cannot be an articulation point, right? Now let me add one more child of U, which does not have this property that I have been discussing so far. Let's say there is another child of U. Let's say V3. And again, it may have a non-empty subtree rooted, I mean, they can be a non-empty subtree rooted at V3. And again, we notice all the back edges which are going from the subtree rooted at V3. And what we see is that the back edges are not going to any ancestor of U. So I'll have some back edge and you see at the most it reaches U. Okay. But there is no back edge which is going to an ancestor of U. What about, so if this is the case, if vertex U indeed has a child, okay, and if you look at the subtree rooted at that child, all the back edges at the most they come back to U. There is no back edge which is going to an ancestor of U. Here if I remove U, do you see that the graph gets disconnected?
Yes, ma'am. The
Yeah,
subgraph rooted at V3.
yeah, right. So if I remove U here, so let me copy this figure, show you. In this case, if I remove U, so all these edges will get deleted. The back edges ending at U gets deleted. The graph clearly gets split into two components. Okay. This is a separate component now. So can we identify, if a vertex, which is neither a root vertex or a leaf vertex, we should be able to identify whether that vertex is an articulation point or not based on the information coming from the back edges, starting from the subchildren of, from the subtrees associated with the children of that node. Is this part clear to all, the third case?
Yes, ma'am, it is clear.
Yes, ma'am.
Sarvesh? Okay. So let me write down that in words. This is the third case. For any other node V, let's say U, so we want to say that U is an articulation point if and only if there is a Uh, so for any other node U is an articulation point or is a cut vertex if and only if U has a child V such that the subtree rooted at V has a back edge or has no back edge to an ancestor of V. Should have no back edge to an ancestor of V.
Could you please repeat the first and third?
Yeah.
First case and third case.
To an ancestor of U. So the first case was root node. You mean this first case?
Yes, ma'am.
So root is a cut vertex if and only if it has two or more children. Okay. So if it has only one child, then it cannot be a root vertex. And leaf node can never be a cut vertex. Those were the first two cases. Is that clear, Sagar?
Yes. Actually, I want to know the reason of the first one. I don't. I'll
Last time
check
you
the
had
recording.
explained this.
No.
The last time you had given an explanation for these cases.
Okay.
Yeah, you should be able to follow this. The
Okay.
key, since the key point is third, and I want to finish this, so let me not spend too much time here. These are easy cases. Okay, is the third case clear to all?
Yes, ma'am.
Yes. So now, theoretically, we can, if I am given a graph, I want to identify the articulation point. The way is you do the DFS on that graph, and now for the when you do DFS, you'll get a single DFS tree. Look at the root, you'll be able to say whether it is a cut vertex or not. Look at all the leaf nodes, you'll be able to say that they are not cut vertices. And for any internal node, which is not a root node, you apply this property, right? For every node, you just look at their children and see if there is a child from where, the child subtree from where there are no back edges going to the ancestor of that node. So if there are no back edges, then it means the node is an articulation point. So you can repeat it for every vertex in the DFS tree. Okay. So how do you implement this? How do you implement this part? Should I leave that for you people to figure out?
Ma'am,
And maybe what I'll
can
do
we
is, please go ahead.
can can we use BFS DFS, or I've heard of this one, ma'am, I think Prince or Kruskal,
Uh, what is the connection with Prim's and Kruskal's algorithm here?
they are used for this I think connectedness or something.
No, that is used for finding the minimum spanning tree. So Prim's and Kruskal's algorithm is used to find the minimum spanning tree of a graph, and that in fact minimum spanning tree with for a weighted graph. Here we don't even care about weights. All we have is whether there is an edge between two vertices or not, and it must be undirected. Okay, so Prim's and Kruskal's has nothing to do with this problem. When I say that you implement this, what I really want is for every node, you want to answer the following question. You want to maintain the following information. That if I look at the nodes, which, how do I put it? So look at all the nodes which are below this node, okay, in the tree. So for instance, for this node, I want to maintain some information. So what information I really want is for all the nodes which are below this node, how high I can go, right? So for instance, there are 3 subtrees below this node. Okay, so it has 3 children, so there are 3 subtrees. Now from the first subtree, I can go up to this node. Okay, so every node has a start time. So I will maintain the start time of every number, right? So start and finish, but I don't care about the finish times now. I just have the start numbers associated with every number. So I'll maintain some information with vertex u. One is what time when do I start exploring this node? So that is the start time. I also maintain another information, which is if I take one or more tree edges and then take a back edge, how high I can reach in the tree. What is the start number of that node? Okay. So for instance, via this subtree, I can reach at the most to this node. So whatever is the starting number of this node, I'll note it down. Then from this subtree, I can reach even higher. Right? So this will override this information. I'll prefer the starting number of this node. Okay. And from this subtree, I can only reach the node u, none of the ancestor of u. So the maximum high that I can go is the starting number of this node. So that information I want to maintain for every node. And once I have that information, I should be easily able to answer whether a node is an articulation point or not. So as we go down the tree, we know that the starting number keeps on decreasing, right? So let me call that information as low of a vertex u, right? So low of u means the DFS number or the start number or the start time, just call it number, so that lowest number of lowest numbered vertex x such that there is a back edge from a descendant of u to x to the vertex x, from a descendant of u to x. Is this low of u, the definition of low of u clear? So for every vertex, the one information I have is the starting number of that vertex. Okay. Some text also call that as the DFS number. In the course lecture, Professor Madhavan refers to it as the pre-number. Okay, so pre-DFS start number. So what I want is for a vertex u, I also want to maintain this low of u. And what this low of u is telling me is, I have this vertex u, it will have number of descendants, right? If all the vertices which are in the lower levels of this tree, they are the descendants of u. So for take any descendant, consider every descendant of u and look at the back edge where it is going. It will go to some vertex x and note the DFS number of that vertex. So pick the lowest DFS number that you can reach from u via a descendant of u. So that number is the low of u. So again, in this example, if I want to know the low of u, it's going to be the DFS number of this word, because that is the lowest DFS number or start number I can reach from u. How? By taking one or more tree edges and then taking a back edge. So is the definition of low of u clear? basically from you, how high I can go via a descendant of you. That is all I'm maintaining.
Ma'am, can you just give an example, ma'am?
That is what I'm telling, right? So suppose I want to know the low of u. So what I will do is I look at all the descendants of u. Okay, so this whole entire subtree is the set of one set of descendants of u. From this subtree, you will see some back edges going to u or some ancestor of u, right? So look at all the back edges, but just keep track of the one which is going as high as possible, because that node will correspond to the lowest start number. So I mark this, I mark the start of this node. Then for the second uh, child of u, again I look at all the nodes which are there in the subtree. Look at all the back edges going from this subtree. Just note the one which is going to the lowest DFS number, lowest start number. Okay. So I have the DF start numbers of these two vertices. And from the third child, I see that there are the highest, the back edge which is taking me uh, to an ancestor of u. There is no back edge which takes me to the ancestor of u. The highest or the one that takes me to the lowest start number is this back edge, which actually is the start number of u. So among all these three nodes, which one will have the lowest start number? The first or the second or the third? Which node will have the smallest start number?
The first one.
First one, right? So I will assign low of u to be equal to the start of this node, starting number or the DFS number of this node.
Okay, ma'am.
Should I run DFS on this graph and then show how does this low of u?
Yes, ma'am. Yes, it would
Okay,
help.
maybe, yeah. Okay, so let's take this example, run DFS, and then we'll maintain start numbers and low of every vertex. Huh? So let's say the start and finish time, those I'll denote by blue color, and the low I'll denote by red color. So let's say I start with A, vertex A. Okay. Then I explore, I go to B. From B, I go to C. From C, I go to E. From E, I go to F. From F, I see a back edge going to C. And we are done with F. So let me assign the start and finish numbers. So I start A at time 0, B at time 1, C at time 2, E at time 3, F at time 4. At time 5, I'm done with F. I come back to E. Okay. From E, E is done, right? So I'm done with E at time 6. And go back to C. From C, what will we do? We'll explore and vertex which is not yet visited, right? So D is not yet visited. I go to D. So what time I'm visiting D? At time 7. From D, I visit G at time 8. From G, there is no other vertex that I need to visit. So I'm done with G at time 9. Go back to D. From D, so D has 3 neighbors, C, B, and G. C is already visited. G is already visited. right? And those are tree edges. The remaining edge is going to be a back edge from D to G. This is a back edge. Okay, but I'm done with D at time, what time? 10. Come back to C. Now I have explored all the vertices from C. And which are the back edges now? Which are the back edges from C?
C2A will be a back edge.
Yes, C to A is a back edge.
And C2B as well.
Oh, C to B is a tree edge.
Oh, yes, yes, yeah.
Yeah, C to B is a tree edge. So anyways, I'm done with C at time 11. And go back to B. From B, there are 3 edges. All of those have been marked. 2 are the tree edges. No, from, yeah, 2 tree edges and 1 back edge. I mean, going forward to D. So B, we finish B at time 12 and A, we finish at time 13, right? So those are the start and finish times. Now I want to know the low for every node, okay? So initially, I will assign the low of a node equal to the starting number of that node, because I can, at the means I know that I can reach that node from, I can reach a node X from X, right? So I say, okay, low of A is equal to 0. Then come to B. Now I want to find, okay, in fact, let me define the low, compute the low in the bottom up fashion. That is how we are actually going to do it when you implement it. So what is the low of F? F is a leaf node. What is the low of F? See, from F is a leaf node, and you see that there is a back edge which takes me to C. And C ka start number is 2. So what is the low of F? See, it's very simple here. Low of a vertex is basically, if it's an internal node, so you will take some 0 or more tree edges in the, when you will go to a descendant of that vertex, and then via back edge, you will reach some ancestor. So whatever is the DFS number of that node is the low of that node, is the low of the internal node we started with. So F is a leaf node. So there is no descendant of F, right? So all you need to see is, look at all the back edges starting from F. Here there is only one back edge. And if there were multiple back edges starting from F, you would have taken the back edge which takes you to a to the highest level in the tree, or the node which has the smallest starting number in the tree. So what is the low of F?
2.
2, right? So there is only one package coming from F. It is taking me to a node C whose start number is 2. So low of F is equal to 2. What about the low of G?
It is 7.
No, it's 8, right? So it's not a back edge, because this is a tree edge. There is no back edge starting from G, right? So its low will be equal to the start number of G. So that is 8. Okay. Now come back to the nodes at the, what do you say? I mean, the parents of the leaf node. So let's look at look at the low of E. What is the low of E?
It is
So in
3.
okay, we initialize it to 3, but is it possible to reach a node which has a lower DFS number via one or more tree edges followed by a back edge? So E has only one child, okay? There is only one descendant. And I see that from that child, I can go to a node whose start number is 2.
Yes, ma'am.
So the low of E is equal to
2. It will be 2.
2. Will be equal to 2. What about the low of D?
It's 7 only.
It will be 1 because it has a back
Oh,
edge.
1.
Yeah.
Okay.
One.
From D, you see a back edge to B, right? And there is only one back edge. So look at all the back edges and just take the starting number of the node which has, I mean, take the smallest starting number. That is it. Okay, so D has a low of 1. C,
0.
0.
so yeah, right. This, if I look at the children of C, they have a low of 1 and 2. But from C itself, there is a back edge to the root node, and therefore the lowest start number that we can reach from C via 0 or more tree edges followed by a back edges, that is equal to 0. So C has a low of 0. What about B? Quickly answer this.
0 only.
0.
1.
No. So initially it will be 1, like if you want to really implement it and during implementation compute low, it will be equal to 1. But then the thing is, from B, I can take this tree edge and then take this back edge.
Okay, ma'am.
Okay. So
So,
this
ma'am,
is
in
also
order
equal
to
to
keep track
0.
of low of a particular node, are we
Mhm.
starting from the leaf and going to the upward?
Yeah. So you run DFS, and in your DFS implementation itself, you have to uh, make write some statements where you are going to update the low of u, low of that vertex. So whenever you start exploring a vertex, initially low of u will be equal to the DFS of u. And once you are done with the descendants of u, you know that you will have the information about low of the children of u. Using those numbers and any back edges that is going from the node u to, to an ancestor, based on those numbers, you will be able to identify the low of the current vertex. So the final low values for nodes will be computed in the bottom of fashion when you're, uh, you know, so the DFS, you start from the root node. Once you reach a leaf node, you are done with that, right? So when you are done with that node, that means you have already computed its low. Similarly, then you come back to the parent node. So for computing the low of the parent, you already have the information about the low of its children. Also, you know that every other edge, which is a back edge starting from the current node, will take me to some other node, right? So using those numbers and the low of its children, you should be able to compute the low of E. Here I've just given an example of how to do it manually, but you can implement it easily. So at least manually how to do it, is this clear to all?
Yes, ma'am.
Yes, ma'am.
Yes,
Anand,
ma'am.
Sarvesh. Okay, what I will do is, since we are running out of time, I will also write how to implement, how to, update low of u when you want to, if you really want to implement it during your DFS calls. So how do we initialize low of u? So initialize, just initially the low of a vertex will be equal to the DFS number of that vertex. And then based on, you just have to look at all the lows of the children of a node and the back edge that is going from that node to any of its ancestor, and based on the lows of those numbers you will be able to compute the low of u. So I'll write it down here and then upload it in the drive. So you'll be, I mean, if there is any confusion you can ask me in the next session, but that is how we will, I mean, if you understand how to manually do it, you will be able to understand the whatever I write here. So
Okay.
if the currently, like the definition and how do we manually compute it, if that is clear, now for this third part, right? For any other node u is a cut vertex if and only if whatever property we have mentioned here is true. Can we write this in terms of the low value? So for any other node u, I want to say that based on these low values, when will U be a cut vertex? U is a cut vertex if when.
And if the low of U will not be less than the current low, like it should not
Not
be
low
lesser
of
than.
U. You are partially right, not the low of U, but if there is a child, let's say V of U, whose low is, I want to look at the low of a child of U, and its low should be, look at this figure now. So in this figure, U is a cut vertex because it has a child. What is the low of this child?
It is equal to the low of U,
It's equal to the DFS number of U.
DFS number. Yeah.
Yeah. And what about the remaining children? Their low is, their low is,
Uh,
how do they compare with the DFS number of U?
they are
Smaller than the DFS
smaller
numbers
than
of U,
the. Yes.
right? For every other child, I see that their low will be smaller because of this back edge, right? Their number is smaller, their low number is smaller than the DFS number of U. But then there is a child whose low is at least the DFS number of U. So whenever we have a case that, for a vertex U, if there is a child V of U such that its low is at least the DFS number or the start number of U, then we say that U is a cut vertex. Clear?
Yes, ma'am. It is clear.
Sarvesh?
Yes, ma'am.
Yeah. So, yeah, so that is how we are going to identify all the cut vertices of a graph. Okay. So you just need to do one DFS on the graph and then maintain these low values, and then you'll be able to answer whether a node or a vertex or a node is a cut vertex or not. Okay, so based on these low values, you should be able to answer for every node if it is a articulation point or not. Okay, so let's stop here. I'm sorry that we took extra
Ma'am,
time,
how
but I
many
wanted to
sessions are
finish.
how many sessions?
Okay, let me first stop the recording now. I have a medical appointment as well. Thank you all for attending. I'll stop the recording now.
Thank you.